Hi gentlemen, and welcome back to Pre-Calc. Today we're going to be moving on to Class 5, Properties of Logarithms, a continuation of the introduction to logarithms from the last class. If you recall from the last class's discussion, logarithms are really just exponents. The logarithmic function is the inverse of the exponential function. Recall, exponential functions come in your form of y equals b to the x, and our log functions come in the form of y equals log base b of x. These two are just inverses of one another. So when we're dealing with logs are exponents. So if you want to know the properties of logs, you actually first need to know the properties of exponents. Recall, when we have x to the a times x to the b, the bases are the same, we're going to take those exponents and we're actually going to add them. That's going to be x to the a plus b. If I have x to the a divided by x to the b, again, bases are the same. We're going to take those exponents and we're going to subtract them, x to the a minus b. That's how we write it as a single term. Also, recall, if we have x to a power raised to another power, we're going to take those exponents and we're going to multiply them. That's going to be x to the a times b, or x to the ab. These rules are actually very important for us to figure out these properties. Before just giving you the properties and filling in a table, guys, let's take a little exploration. Let's say I were to give you an expression for x. And let's say x is going to be equal to log base b of r. Let's give you another expression for y. Y is going to equal to log base b of s. Notice x and y in both of these cases are logarithmic expressions. Or equations, I should say. They're not really expressions. What if we take both of these equations and convert them from log form to exponential form? Recall that we have our base. In this case, our base is b. Our base is going to be raised to our exponent, in this case, which is x. And that's going to equal to the argument, or r. We can do the same thing for the second equation. Your base, again, your base is b, raised to your exponent. That's going to be the y. And it's going to equal, again, to the argument, or in this case, that will be s. What we want to do is we want to take a look here and we want to say, well, what happens if we take r and we multiply it by s? If I have r and I multiply it by s, we can rewrite that as b to the x times b to the y. Notice both of these bases are the same, so we can take that and we can write it as b to the x plus y. Note, this is still an exponential equation. Our base here is b, our exponent is x plus y, and it's going to equal to rs, or r times s. What if we were to take this equation here and actually write it in logarithmic form? If we write this in logarithmic form, we can use our log. Note that our base here is b. Okay, we will have the argument on the inside, or the number that it was equal to. That will be our rs. And it's going to equal to your exponent. It's going to equal to your x plus y. Well, let's think about this for a second. We actually had an expression for x, and we actually had an expression for y. Let's rewrite this for a second, okay, as log base b of rs, and let's replace that x with log base b of r. Plus the expression for y, or log base b of s. If you take a look here, we took a singular log expression, and we wrote it as the sum of two separate logs. This works because inside the first log, the r and s are being multiplied. If inside the logarithm they're being multiplied, we can separate them by using addition. That would make sense. Recall from before, if we have two exponents that are being multiplied, we can combine them or deal with them by using addition. This works, gentlemen, for most logs. Just note, as long as the bases are remaining the same. So we actually are going to have three rules for logarithms: multiplication, division, and powers, just like we saw above. If you have log of A times B, we can rewrite this expression as two different logs by writing log of A plus log of B. Notice there are now two terms with logs. Okay. One has the first factor and the other one has the second factor. Notice that the base here, even though not written, would be a base of 10. Recall from last class that we call that a common log. So notice if the original expression given to you is a common log, that when we separate it, both of those logs are also going to be common logs. We can also write this using a different base, like for instance, what if we use a natural log or ln? If we have ln of AB, just like above, it'd be no different. We'd have ln of A plus ln of B, separating that multiplication by using addition and putting it into two separate logs. If you take a look at the next term here, where we are dividing, if you hypothesize that we're going to separate them using subtraction, then you'd be correct. This is going to be log of A minus log of B. Again, note that the bases have to stay consistent. If we had the natural log of A divided by B, that would be the same as ln of A minus ln of B. Again, as long as the bases stay the same. This last law is actually one of the most important laws that you're going to come across in terms of logs. When we're dealing with this, you'll see it this year, you'll see it in the next lesson while solving equations, you'll see it in calculus. It will continue to come back over and over and over again. When you take a look here, notice that x is being raised to a power. When we raise a base to a power, we would multiply. For that idea, we're going to take this exponent and we're going to move it out front as a coefficient or multiply it to the log. So if you have log of x to the a power, that's going to be the same as a times log x. Note, as long as the bases stay the same. So if we had ln of x to the a, that would be the same as a ln of x, or a times ln of x. So you might be saying, well, you're telling me what these rules are, but do they actually work? And I'm going to say, yeah, they're actually going to work. So if you take a look here, notice we have decimal approximations for each of these log expressions. Log of 2 is approximately 3.0103. Log of 4 is given as an approximation, and so is log of 8. You can justify them in your calculator if you'd like to check. If you look at the first expression here, it's asking you for log of 2 times 4. Notice with multiplication, we can rewrite this as log 2 plus log 4, using addition to separate the two factors into two separate logs. If that's the case here, this would be 0.30103, and we'd be adding 0.60206. If you add those two expressions, you do wind up 0.90309. That actually makes sense, because if I took the 2 and the 4 and I multiplied them initially without separating them, that would give me 8. And if you look at the approximation right over here, log of 8, that is equal to 0.90309. So it does work. That does make sense. In addition, we can justify the same by looking at the next question where it says log of 8 divided by 2. That expression can be written as log of 8 minus log of 2, right? Division became subtraction into two separate logs. Log of 8 is approximately 9.0309. Log of 2 is approximately 0.30103. And if you subtract those two expressions, you'll get 0.60206. And again, that would make sense. Because if we look at that expression there, that value, okay, that would be the same as having log of 4, because 8 divided by 2 is 4. And if you look at that value, it matches. It's exactly the same. In addition, we can look at the last one here and say, hey, we have 2 raised to the third power. This exponent inside the log is going to come outside as a coefficient. This would be like saying 3 times log 2. The given value for log 2 is approximately 0.30103. If we take that expression and we multiply it by 3, we get 0.90309, which, hey, that's the same as log 8, right? 2 to the third is equal to 8. They're exactly the same. There are other ways that we can also use these properties of logarithms, not just for evaluating, but what happens when we have other logs written as combinations of other numbers? If you take a look here, it says, what if log of 3 was equal to b and log of 4 was equal to a? We would like to write the following expressions, or write the following term in terms of a and b. If you look at log 12, it doesn't say log 3 and it doesn't say log 4. However, we can rewrite 12 as a product of 3s and 4s. What that means is that we can write this as log of 3 times 4. 3 times 4 is 12. If we use our expansion to rewrite that, we can rewrite that as log of 3 plus log of 4. Notice, gentlemen, that this is not log of 3 plus 4. That's not what we're writing. That is the common error here. Please make sure that as you expand them, that you're writing them as two separate logs, log 3 plus log 4. Because if that's the case, now log 3, that is equivalent to b. And log 4, that expression there, that is equivalent to a. So the expression of log 12 is actually equal to b plus a. We can do the same moving down the line as we go to log 27. You can write log 27 as a product, again, of 3s and 4s. I look at 27 and I know 27 is 3 to the third. I look and I see that I have an exponent here. This exponent can be moved in front as a coefficient. That would be 3 log 3. Again, we see that expression there for log 3, and we can turn that into a b. So this would be 3 times b, or 3b. If you look at the next one for 30, you might be saying to yourself, how am I supposed to do that? There's no products of 3 and 4 that make it to 30. And I actually happen to agree with you. However, if we think about it and we look at this log really close, notice that it seems that there's no base on that log. If there is no base on that log, that really means that the base is 10. It's a common log. That means that we can also use factors of 10 to rewrite this log. We can rewrite log 30 as log 3 times 10. Using addition to separate those into two logs, we have log 3 plus log 10. Log 3 we know is b from above. And log 10, recall, if you want to evaluate log 10, you're basically saying to yourself 10 to what power is going to give us 10, right? So you're saying 10 to what power is going to give you 10? And that would be to the first power. So that expression here, this turns out to be 1. So overall, log 30 in this question here would be equal to b plus 1. We can do the same with log 400, and we can write that as log of 4 times 100. Notice again, the base is 10, so we can use powers of 10. That would be the same as log 4 plus log 100. We know that log 4 is equivalent to a from above, and log 100, in order to evaluate that, ask yourself, 10 to what power is going to be 100? Remember, that meant that your base was 10. 10 to what power is going to give you 100? And that would be 2. So log of 100 is equal to 2. This expression, therefore, is equal to a plus 2. So far, we've covered 3 rules: adding, subtraction, and powers, right? Adding came from multiplication, subtraction came from addition, and powers, we used multiplication. We also not only want to evaluate 2 logs here, or expand them using evaluating variables, but what if we want to expand logarithms and condense logarithms? So we want to take a singular log and rewrite it into multiple logs, or take multiple logs and rewrite it as a single log. If you look at for the first one in example 3, notice that all the terms in example 3, we have log 8x y to the 4th. All of those are being multiplied. This is being multiplied, this is being multiplied. Since they're being multiplied, we can expand this logarithm by using addition. We will have log 8 plus log x plus log y to the 4th. Notice that the original base that was given, which was a common log, continues to all 3 logs. The only thing left that you need to handle is we need to take this exponent and move it to the front. Once you deal with any multiplication or division, as you'll see in other examples coming up, you just want to take the exponents and move them to the front. So here we would have log 8 plus log x plus 4 log y. That would be your final answer. That would be the full expansion, separating out multiplication and division, and then finally dealing with exponents in your final step. If you take a look at the next example here, notice that overall we have division. With division, we're going to separate that using subtraction. So this would be the same as having this ln of x squared plus 5 minus ln of x. Note though, with that radical, we can actually clean that up a little bit more. Remember, radicals, or square roots specifically, have an exponent of 1/2. We can take that exponent and just move it in front. So this would be equivalent to 1/2 the natural log of x squared plus 5 minus the natural log of x. That would be your final answer on part B. Notice that when I started with my original function here as the natural log, we continued through as we expanded where every single term had to keep that expression for the natural log. If you look at the next one here, okay, log base 4 of x to the 3rd minus y squared, we're going to continue through here again using our division. We're going to use subtraction. We have log base 4 of x to the 3rd minus log base 4 of y squared. The only thing left to do here is to take your exponents and move them out front as a coefficient. This would be like saying 3 log base 4 of x minus 2 log base 4 of y. This would be our final answer expanded. Notice when we're done doing the expansion, There are no exponents on the terms in our logs. They've all been moved to the front as coefficients. What happens, though, when we want to go back in the opposite direction? What happens when we have it expanded and we want to go back? Remember, we were kind of saying, well, let's deal with any multiplication or division first, and then we dealt with any exponents. Well, when we're going to do condensing, we're actually going to want to do it in the opposite direction. We're actually going to first want to deal with our exponents, and then we're going to want to deal with any multiplication or division that we see going on. So if I take a look at example A right here on this question, notice we're going to have to take these coefficients and move them back as exponents first. That means that we have log x to the 5th minus log xy squared. Once we have that, and we see that there's subtraction in between, we can now rewrite this as one single log. We can write this as log x to the 5th divided by xy squared. Note that this is not equal to log x to the 5th divided by log xy squared. Don't be that guy. Don't make that mistake. We are taking two separate logs and writing them as one singular log. If you'd like to clean this up a little bit further, what we could do is we can actually just take this denominator here and distribute that exponent, or rewrite it as x squared y squared. That would be equivalent as well. Again, if we go on to number B, just make sure here, gentlemen, that we're taking our exponents first and moving them back. Okay, we have the natural log. Now remember, 1/3 as an exponent, that just means that we have a cube root of x. So rather than writing it as a fractional exponent, it'd be nice if we rewrite that with a radical. We have the ln of x plus 1 to the 4th. Notice in this case now, we have addition. So when we combine that again to one singular log, we're going to use multiplication. This will be the cube root of x times x plus 1 to the 4th power. Notice it's written as a singular log and all the bases stay the same. If you look at the next example here, it looks very similar, but certain things have changed also. Again, we still deal with our exponents first. Let's take those exponents and let's move them back. So we would have the natural log of the cube root of x minus the natural log of x plus 1 to the 4th minus the natural log of y. If you look here, notice that the last two terms are being subtracted. So how do we handle this when we have more than one term, more than two terms, and we're trying to combine them? Well, here's the thing. If you combine the first two, right, and we use our subtraction here to turn it to division, we'd have what we'd have look like this. We'd have the natural log of the cube root of x over x plus 1 to the 4th. Then we'd be subtracting still the natural log of y. Notice, if we're taking this expression and we're, again, dividing by y, what's happening is that y is just going to wind up in our denominator. We have the ln of the cube root of x over x plus 1 to the 4th times y in your denominator as a single one. You might be saying, well, why is this happening? Why does that y wind up in the denominator? Why is that subtraction telling me that it's going to go down there? Well, you can say to yourself, well, what if we have the cube root of x over x plus 1 to the fourth, and I divide that by y. Remember, when you're dividing by y, okay, it's just like multiplying by the reciprocal. So you'd have the cube root of x over x plus 1 to the fourth. If I multiply that by 1 over y, notice that the y is staying in your denominator. So as I write it as a single log, okay, if it has that subtraction sign there, for the most part, it's going to wind up in your denominator. So we've now covered the properties of logs with addition, subtraction, and powers. One more last thing we need to cover is what we call a change of base. Sometimes when we deal with logs, right, they're written in a more complicated form. Notice on your calculator, if you look at the buttons on there, there's only buttons for natural log and log. There really aren't buttons there for if you have a base that's not e or 10. So the question is, what happens when we have expressions like log base b of x? How are we going to be able to rewrite those expressions there? Well, there is definitely one way that we can rewrite those expressions, and we can do it by changing the base. If you have log base b of x, notice it almost looks like the x is quote-unquote on top, and the b, in a way, is quote-unquote on bottom. If that's the case, you can actually rewrite that expression in another format. You can rewrite that as log x divided by log b. As long as this base on top matches this base on the bottom for those particular logs, you can separate it by putting your x as your argument on top and your b as your argument on the bottom. You're probably saying, how did you do that? Where is that even coming from? Well, let's take a second and let's do a little bit of an exploration here. If I were to give you an expression like 4 to the y, and I let that equal to 7, okay, we can actually take the natural log of both sides. Remember, whatever we do to one side, we can do to the other. It's like squaring both sides or square rooting both sides. We can rewrite that as the natural log of 4 to the y is equal to the natural log of 7. Recall, if we have exponents just like that, we can actually move them to the front as a coefficient. So this is like saying y times the natural log of 4 is equal to the natural log of 7. If I were to be solving for y, or dividing both sides by the ln of 4, so if I divide by the ln of 4 and I divide by the ln of 4, that would produce that y is equal to the natural log of 7 divided by the natural log of 4. Well, if you hold off for a second and we think back about this original expression, if I were to write that in log form, that would mean that log base 4 of 7 was equal to y. So what you're saying to me here is if I have y, which is y, they're both exactly the same, that we actually have here that log base 4 of 7 is equal to the natural log of 7 over the natural log of 4. Again, if we have this singular log, here, where the base is not a nice number, or if it's not in terms of ln's or in terms of a common log, we can actually rewrite that expression as the division of two logs by taking the argument or the inside and placing that on top, and taking your base, that's your bottom, and placing that as the argument on the bottom. As long as we rewrite it, that the two logs have the same base. So as we continue on and we look at these last three examples, okay, if you want to take this and rewrite this as two separate logs, okay, by changing the base, let's say I wanted to change it so the base was a common log, Okay, so it was a common log. We can rewrite this as log 16 divided by log 3. That actually might make it a little bit easier for us to put that right into our calculator and evaluate, because those buttons are right on our home screen. If we have log of 16, don't forget to close your parentheses on that 16 and divide by log of 3. That's actually going to produce a value of 2.524, just rounding it to the nearest 10,000. We can do the same here, but suppose I didn't want to use a common log, but I wanted to use a natural log. If that's the case, we can rewrite this as the natural log of 10 divided by the natural log of 6. If I do that and I use the natural log of 10 and I divide that by the natural log of 6, that's just going to give me 1.28. We'll round it up to, or keep it to 5. Now, if I look at this expression, though, and I say, maybe natural log wasn't the best decision to make here. What if we decided to use a common log? Notice that that would be log 10 divided by log 6. We know log 10 has a value of 1. So if I rewrite that as 1 over log 6, just going to move that over so we have a little bit more room here. If we write that as 1 over log 6, and we find that value, again, just 1 divided by log of 6, that will also give us 1.285. So again, we're getting that same value here on our calculator no matter what version we use, as long as we separate it into two common bases. If you look at the next one here, this one is actually really interesting, this problem, because if I write that using common logs, okay, we can actually rewrite this as log 2 divided by log 1 divided by 2, or a half. Hold on. Let's think about this for a second. If I have log 2 on top, right, that's going to stay log 2. However, if we look at the bottom, notice that 1/2 is really division. What if we separate this to log 1 minus log 2? If you recall, log 1, you could ask yourself 10 to what power, right? 10 to what power gives me 1? Well, we know that's to the 0 power. So this expression here is really the same as log 2 over 0 minus log 2. Or really, log 2 divided by a negative log 2. Well, if we have log 2 divided by log 2, that's just 1. This expression is actually just equal to -1. And why does that really make sense? Well, if we come back and we think about it, log base 1/2 of 2, recall from the video from the other day, it's really like asking yourself 1/2 to what power is equal to 2. If you want to bring that 2 back up so that it's not in your denominator anymore, remember that 1/2 just to that negative first power. We'll make this as 2 over 1 to the positive first, or just 2. So making that exponent into -1 would produce 2. So this expression is -1, and that makes sense. That's what we just proved again with that change of base equation. So just to review, guys, today we went over properties of logs. We rewrote logs using those properties. We expanded, we condensed, and we also learned our change of base formula. You have a worksheet with all of these notes blank for you to follow along with. And right at the bottom of this sheet will be some practice for you to conclude for your classwork, and you continue on from there, completing these examples. Good luck with this, guys. Enjoy your homework, and we'll speak soon.